Good afternoon. My name is Damanpreet Singh, and my topic for today's presentation is alkylation process. So let us begin. So first we have the introduction to the topic, which is alkylation. Alkylation is one of the most important organic reactions which is used to produce many industrially vital and important products. This process has been utilized over the last few decades. The alkylation processes are generally directed towards the production of high-octane liquids for aviation gasoline. Based on the type of the catalyst used, there are two types of alkylation: sulfuric acid and hydrogen fluoride. The sulfuric acid process was first introduced in the year 1938, while the hydrogen fluoride alkylation was introduced in the year 1942. In petroleum refining, alkylation is defined as the chemical process in which light, gaseous hydrocarbons are combined to produce high-octane components of gasoline. The light hydrocarbons consist of olefins and isoparaffins. These compounds are fed into a reactor where, under the influence of a sulfuric acid or hydrofluoric acid catalyst, they combine to form a mixture of heavier hydrocarbons. The heavier hydrocarbons are then separated in a fractionating column. This is the general overview of the alkylation process. Alkylation can also be done in the absence of the catalyst as well. Alkylation is generally catalyzed by a strong acid, that is either sulfuric acid or hydrogen fluoride. In the absence of catalyst, alkylation between isobutane and olefin is possible, but it must be run under severe conditions, that is, the temperature should be as high as 500 degrees Celsius and the pressure should be between 200 to 400 bar. In the presence of an acid catalyst, the reaction temperature is quite low. It is generally lower than 50 degrees Celsius, and the pressure also drops significantly. The pressure required is lower than 30 bar. The major difference in using either acid is that isobutane is quite insoluble in sulfuric acid, but it is reasonably soluble in hydrofluoric acid. So thus this requires the use of a high isobutane olefin ratio to compensate for the low solubility in sulfuric acid. Furthermore, the reaction must also occur at a low temperature to compensate for the solubility. So this is the block diagram of a general alkylation process. So as we can see, isobutane and olefins are fed to the reactor where the acid catalyst is present and the alkylation process takes place. After the reaction has occurred, the acid is separated in the acid settler and is then recycled back to the reactor, whereas the heavier hydrocarbons are then sent for product separation in a fractionating column. The products thus produced are LPG propane and butane alkylate, while the isobutane is recycled and sent back to the alkylation reactor for further processing. So now we have the first type of alkylation, which is the sulfuric acid alkylation. In sulfuric acid alkylation units, the feed generally consists of propylene, butylene, amylene and fresh isobutane. The feed enters the reactor and then makes contact with sulfuric acid at a concentration of 85% to 95%. Divided into zones. The olefins are fed through distributors to each zone, and the sulfuric acid and isobutanes flow over baffles from one zone to the next. The effluent from the reactor goes to a settler in which hydrocarbons are separated from the acid. The acid is returned to the reactor. The hydrocarbons are washed with caustic and sent to fractionation for the separation of the different hydrocarbons. The fractionation section comprises of a depropanizer, a deisobutanizer, and a debutanizer. The alkylate from the deisobutanizer can go directly to motor fuel blending, or it can be reprocessed to produce aviation grade gasoline. The fractionation section is used for the separation of the hydrocarbons into the various components. So the following is the block diagram of a general sulfuric acid alkylation process. So as we can see, the olefin feed is fed to the reactor where sulfuric acid acts as a catalyst and the alkylation process takes place. The hydrocarbon vapors are sent to the compressor for condensing, whereas after the process has taken place, the acid is recovered and recycled back into the reactor, whereas the heavier hydrocarbons formed are sent to the fractionating section where they are separated into the various components, that is butane, alkylate. The isobutane recovered is also recycled back to the reactor so as to make sure that we have the most efficiency possible. So next we have the second type of alkylation, which is the hydrofluoric alkylation. In the case of hydrofluoric alkylation, olefins and isobutane are first dried and then fed to a reactor, where the alkylation reaction takes place in the presence of a hydrofluoric catalyst. The effluent from the reactor flows to a settler, where the acid phase separates from the hydrocarbon phase. The acid which is separated is drawn off and then recycled back to the reactor. Meanwhile, the hydrocarbon phase goes to a deisobutanizer in the fractionation section. The overhead stream, which consists of propane, isobutane, and residual HF, goes to a depropanizer in the fractionating section. The depropanizer overhead goes to an hydrofluoric stripper so that we can recover the HF acid, which is used as a catalyst, and it is recycled. The overhead is then treated with caustic and is sent to storage. Isobutane from the deisobutanizer main fractionator is recycled back into the reactor with HF catalyst. The bottom stream from the debutanizer goes to product blending, and the isobutane recovered is also recycled back. So this is the block diagram of a general hydrofluoric alkylation process. So as we can see, olefins and isobutane are fed to a reactor where HF acts as a catalyst and the alkylation process takes place. After this, the acid is recovered in a settler and then sent to a regenerator, after which it is recycled back into the reactor. The hydrocarbons are then sent to an acid stripper where any residual acid left is also recycled back. After this, the hydrocarbons are sent to the fractionating column, which consists of the depropanizer, deisobutanizer, and debutanizer, so that the hydrocarbons can be separated into their various components which are propane, N-butane, alkylate, and isobutane. The isobutane recovered is then sent back as a recycle. So next and finally we have the applications of the different types of alkylation process. In the oil refining industry, the alkylation process is mainly used to produce high octane gasoline blending components and high octane aviation gasoline. For example, isobutane is alkylated with propylene or butene to give an alkylated oil, which is the earliest application of the alkylation process. Another example is that benzene is alkylated with propylene to produce cumene. So in a conventional oil refinery, isobutane is alkylated with low molecular weight alkenes, that is propenes, in the presence of a Bronsted acid catalyst, which can include solid acids. The catalyst protonates the alkenes to produce carbocations, which then further alkylate the isobutane. The product formed is known as alkylate. It is composed of a mixture of high-octane, branched-chain, paraffinic hydrocarbons. The alkylate is a premium gasoline blending stock because it has exceptional anti-knock properties and is clean burning. Alkylate is also used in the manufacture of an AV gas. Several commodity chemicals and other important chemicals can also be produced by alkylation. It includes several fundamental benzene-based feedstock, such as ethyl benzene, which is considered a precursor to styrene, cumene, which is the precursor to phenol and acetone, and linear alkyl benzene sulfonates, which are used in the manufacture of detergents. So thank you. This concludes our presentation for today.